Hello and welcome. We are Renuclear, and we are here to present a novel approach to reactor decommissioning. I am Thomas Nigl, and I am CEO and Materials Engineer.
I'm Daniel Kelly, I'm our CFO, and I was our business mentor point of contact.
I'm David Hertz. I'm the CTO, as well as the point of contact for our technical mentors.
I'm Chris Puzzo. I'm the Chief Process Officer and the Senior Systems Engineer.
And I'm George Winter, and I'm the Chief Safety Officer and Regulatory Affairs Officer.
So today, climate change is a very significant problem that is affecting the U.S. population and populations abroad. One mitigation path that is popular is the implementation of alternative energy, and specifically nuclear energy. There are two main drawbacks, however, to the beautiful technology that is nuclear energy, and that is it generates highly radioactive waste, and that it also only uses approximately 7% of the fuel that is put into reactors. It's like almost if you take 10 sandwiches, instead of eating 5 sandwiches for fuel and saving the rest for later, instead you take a bite out of each sandwich and then you toss the rest. It's highly inefficient. In addition to these two main problems, the current nuclear decommissioning methods are very, very expensive. For our investigation, we decided to use the Pilgrim Nuclear Power Plant as our case study. Currently, the plant is planned for decommissioning using the safe store method, and overall costs are actually projected to be approximately $1 billion. So in addition to being costly, the timeline also extends such that it is planned to finish in mid-2060, which is 44 years from now. And in addition to both of those, the spent nuclear fuel is supposed to remain in isolation on site, meaning that it is going to be costly, is going to be timely, and is also going to be unsafe.
So we're going to be presenting today another alternative option for decommissioning of a nuclear fuel plant. But to start out, let's discuss quickly the ways that we can decommission a nuclear reactor today. The NRC approves of currently 3 separate strategies for decommissioning a nuclear plant. The first, and historically the most common, is a method called Project Decom, which is also known as immediate dismantlement, in which the nuclear plant is shut down, all of the equipment is moved off-site for processing, as well as all of the nuclear fuel and hazardous wastes are sent to long-term dry cask storage off-site, which is just monitoring the spent fuel over hundreds of years until it's actually able to be decayed to background radiation levels. Much more common recently, and very likely for the current plans for both Vermont Yankee Nuclear Plant as well as Massachusetts Pilgrim, is the method called Safe Store, Project Safe Store, which is known as deferred decommissioning, where the fuel is monitored on-site for approximately a decade in wet storage, moved to dry storage, and still maintained on-site until the government eventually agrees to take over the responsibility to monitor the fuel over a much longer term. The third project that is recognized, Project Entomb, has never actually been used in the United States, but it's more of an emergency available method in which the entire reactor site would be encased in a radiation shielding material such as large amounts of cement and monitored as it is until the radiation emissions have decayed to beyond background nuclear radiation levels.
So all 3 of the methods that David just mentioned have one significant issue. They all deal with decommissioning a reactor, but none of them actually deal with handling the waste you get from that reactor. Spent nuclear fuel is highly radioactive. It also, as Tom alluded to earlier, contains massive amounts of very useful oxides, uranium, thorium, plutonium oxides. One of the ideas for how we can look at this fuel and use it in a useful way is pyroprocessing and electrolysis. Been studied by Argonne National Lab, Savannah River National Lab. The idea here is that you melt down that spent nuclear fuel after you remove it from the cladding, and you're able to use electrolysis to separate out relatively pure uranium, thorium, and plutonium from that SNF while removing the rest of the actinides and rare earths that are present there. Once you do that, you can reoxidize the uranium, plutonium, and thorium into their oxides, which can be sent to a fabrication unit, turned into pellets, and once again turned into fuel rods that can be put into a generating reactor. This is great in terms of recycling, but not terribly great in terms of reducing the lifetime of waste. The actinides and rare earths that you toss out in that electrolysis step there still have massively long lifetimes, and this doesn't really help with that very much. Another idea is molten salt technology, reactor technology, which was mainly looked into at Oak Ridge National Labs in the 1960s and 70s. The idea here is that you remove the SNF from its cladding, you toss it into a very, very high temperature, several hundred degrees C reactor, and what you can do in this situation is restart the fission reactions that break down all of your actinides and rare earths and your lanthanides and generate additional heat for electricity consumption. But more importantly for this method, what you're doing is you're fissioning all of those actinides down to their most stable rare earth components that have the shortest half-lives. And so you're taking waste that has a half-life of a few thousand years, maybe tens of thousands of years in some cases, to fuel that has a half-life of 10 to the 2 years, a couple hundred, much more reasonable challenge to face than 10,000 years.
So our project plan is to combine these two technologies. First, we're going to combine the pyroprocessing technology to remove 95% of the usable fuel so it can be reused. And then we're also going to implement the molten salt reactor, and this will allow us to reduce the lifetime of what is left, the leftover spent nuclear fuel.
And all this culminates as a fourth suggested decommissioning strategy for nuclear power plants, Project Renew. We're going to discuss all of the different process steps that are involved with Project Renew in depth, but first, just on a very higher level overview. We're going to start out with the metal oxide separation steps. That's where you recover a lot of the uranium and plutonium oxides to be reprocessed into new fuel. All of the remaining fission products can be moved into the MSBR, the fission reactor that will be operating on site, to turn those fission products into much more stable, low-level radiation waste, which will be separated out in either the gas separations loop or in our salt separations loop, depending on the characterization of that waste material. And then, of course, operating a fission reactor at critical levels requires the removal of a significant amount of heat, which will be removed using the existing infrastructure already at Vermont or at Massachusetts Pilgrim plant. Just to start out with the metal oxide fuel recovery stage, it's essentially three main steps in the metal oxide recovery. First, the existing SNF is pulverized into a powder that can be sent into a fluorination reactor, where fluorine gas is reacted with the oxide waste to remove all of the actinides as uranium or plutonium hexafluorides, which are gaseous and can be transferred over to the reclamation reactor, where hydrogenation and steam reaction will convert the hexafluoride waste back into a stable oxide, which can be reprocessed as nuclear fuel. The controls on this step, we're going to talk about the controls for every one of the loops we have. And fundamentally, you start out with all of the safety regulation. You have alarms for all of the different feedback sensors, which are, or flow sensors on all of your inlet sources, which ensure that all of your material balances are regulated and that it allows operators to control that well. The flow of powder from the pulverizing step into the initial reactor is controlled to maintain that constant level of the reactor salt. And then the rate at which you're reclaiming gaseous products from that salt is also determined by the level in the tank as well as your flow rate into the nuclear reactor step. So in that nuclear reactor step, this is going to function as essentially the central hub of the entire process. You initially have your salts coming from the fluorinator into the reactor, where you have your nuclear reaction and you're generating those fission products, which will either be separated out as gaseous waste, as salt waste, and then of course you have heat removal to maintain that heat. Our process controls here are relatively straightforward. The height of salt in the reactor is maintained by, again, adjusting the rate at which you're receiving salt from the fluorinator. The rate at which you're cycling through the fission product removal salt step is determined by the radioactivity of the waste being returned to the reactor, which signifies the actinide content of that recycle stream, as well as the heat removal step is generated in order to maintain a constant, stable temperature inside of the reactor for critical operation.
Now, to give you a little idea of how exactly a molten salt reactor works, first you have your dirty uranium oxide, and you insert it into the reactor, and then from there, your uranium oxide is cleaned, and it comes out so that you can reuse it for other nuclear reactors. Now, the waste stays inside and recirculates through the reactor so that the half-life goes from hundreds of thousands of years to hundreds or thousands of years. Now, also, to compare it to light water reactors, our molten salt reactor has no fuel rods. It is operating at a very, very low pressure, almost atmospheric pressure. And also, instead of having a very large pressure release if the reactor has a runaway reaction, we simply have a molten salt plug that if the salt becomes too hot, it melts and it goes into an underground container where it is cooled and contained.
So David mentioned the removal steps that we need. That's really important for our reactor for two reasons. We're continuously processing SNF that's on the site. So in order to continuously load material into our reactor, we need to continuously remove things from our reactor. Now, it's incredibly important that we remove certain elements because they act as what we call neutron poisons. They have such a large neutron absorption spectrum and such a relatively long half-life that they stick around for a lot longer than certain other elements do, and they have a larger tendency to absorb neutrons from the system. What this means is that they're acting as sponges for the energy that's otherwise going to keep our system going. If we allow those sponges to stay around, other than the problems with the mass balances of loading new material in, what we have is a reactor that's no longer operating stably, and that's not safe, it's not efficient. We need to make sure that doesn't happen. So the first thing we have to do is remove the products that are formed as dissolved solids. First thing we do is we pump them into a fluorinator. We use a fluorinator step similar to the beginning of this whole process, where we're able to remove 95% of the uranium as UF6, gaseous UF6. We move that into a separate tank where we can deal with it later. We can't just introduce a gas into the system. We need to turn it back into uranium tetrafluoride. After we've removed the UF6, there's still a little bit of uranium left, and there's also protactinium. By countercurrent contacting in a multi-stage extractor with a bismuth stream that has lithium reductant in it, we're able to remove the uranium and protactinium so that we have a fuel salt that is going into a different part of this loop without those two elements. And we have those two elements in a bismuth stream so that we can deal with them separately. Once we've done that, we convince them to leave that bismuth stream in the presence of a waste salt that will eventually be vitrified and disposed of. We do that by countercurrent extraction with hydrogen fluoride and hydrogen. Once we've extracted the uranium and protactinium, we're able to fluorinate again to remove still more uranium hexafluoride. Once we remove that and move it to the holding tank I mentioned before, we start a loop where we have the protactinium decay into its first decay product, which is uranium-233. As that happens, that is flowing back through the fluorinator reactor, while most of the protactinium stays in this circle, the top tank in that circle there. As the uranium moves back into the fluorinator, we're fluorinating that into UF6, moving it back to the collection tank. At the same time, the protactinium, after 8 half-lives, is almost entirely decayed. We can move that into a disposal tank where we do one last batch fluorination, remove anything in there that might be of use to us. Otherwise, we take all the protactinium that's in that waste salt and we vitrify and dispose of it. Now at this point, we have fuel salt that's going up here into this other extractor. It's clean of uranium and protactinium, but it has rare earths at more or less the same concentration you'd find them in the MSBR. So in order to get rid of those, which is actually most of what we're getting rid of in this step, we countercurrent extract using lithium chloride acceptor salt. That moves all of the rare earths into this rightmost part of the system here, and the fuel salt is able to be recycled up here after we treat the UF6 with hydrogen to make it UF4. We also pass all of this through a nickel mesh to make sure we're removing as many of the corrosive impurities as we can. A big one of those would be bismuth. There's a lot of bismuth in the system. That shouldn't go in the reactor. The nickel mesh makes sure that a lot of that gets removed. Almost all of it gets removed. It's important to say that all the bismuth that we have in here has a reductant in it, lithium. That lithium really helps extract the rare earths and lanthanides from the salts that we have up here. Now, the rare earths that we're removing at this point are either divalent or trivalent. It takes different amounts of lithium to remove divalent and trivalent rare earths. So in order to minimize our lithium usage, we're dealing with them in 2 different extractors here. To remove the trivalents, it takes about 5% reductant. To remove the divalents, it takes about 50% reductant. Almost everything is removed in the trivalent extractor. About 2 to 5% of that stream is then passed into the divalent extractor. At the end of the extraction, the bismuth, lithium, rare earth, lanthanide mixtures are combined together and tossed into that waste salt tank there for vitrification and disposal. To touch quickly on the process controls here, a lot of it's pretty much the same thing, so I'm not going to go too much into detail. A lot of this is flow transmitters on raw materials charging to make sure that we're not overcharging reactors. There's a lot that could go wrong with overcharging, overpressurization. We don't want any leaks from this system. This is a very dangerous system if something goes wrong. So we're making sure we have all the controls in place to prevent disaster. We have similar controls on charging between reactors, not just raw materials. We also have a level sensor on the waste salt container just to make sure we're not overloading that. Our next removal system is a gas removal system. Although most of what we're removing is formed as a dissolved solid, a few things are formed as dissolved gas. Most notably, we have tritium in the system. We have hydrogen fluoride in the system, neon, xenon, krypton, and iodine. So in order to get rid of all of those, we sparge the fuel salt with a helium-hydrogen mixture. Now we're sparging a 650 degrees Celsius reactor, and we don't want those temperatures in this loop. So we have a heat exchanger there after the sparge. Then it goes into first a charcoal bed filter and then a palladium filter. The charcoal bed filter is effective at removing the krypton, neon, xenon, iodine, and hydrogen fluoride. Now it's important to mention that xenon 133 is a decay product of iodine 133, and xenon 133 happens to be the most powerful neutron poison that is in our system. So it's very important to remove both the xenon and the iodine in these steps. The palladium filter is there so that we can recover and hold on to the helium while passing the hydrogen and tritium into the next parts of this system. That helium will then be recycled to the sparging. Next part of this is a cryogenic distillation column for the separation of tritium from hydrogen. There's quite a bit going on here. It's not very easy to remove tritium from hydrogen. This all happens at double digits K, around 28 to 33 Kelvin. So there's a lot of compressing going on for compressive cooling. We start with our outstream at 3.7 atmospheres, and through heat exchangers, there we have the boiling temperatures of hydrogen and tritium. They're far enough apart that we can separate them, but there's quite a bit of effort that goes into separating them. We have a distillation column that's 100 stages and a reflux ratio of anywhere from 2 to 5. 2 should work in all of our calculations, but to be conservative, we priced for a reflux ratio of 5. In order to maintain the very low temperatures we need, we're putting a lot of energy into this system to compress to 14 atmospheres here so that we can pass through expansion turbines and generate expansive cooling streams. We need to make sure that we don't have liquids or gases where we don't want liquids or gases. We need to make sure we maintain very close temperature control of this system so that at the end we can recycle our hydrogen at the top there and we can oxidize our tritium into super heavy water, which will be stored on site until it decays to under 1% activity, which is approximately a 110-year process. Process controls in this part, there's a lot of temperature control, as I said. The most important part of this, I would argue, is the very beginning with the charcoal bed filter. We're adsorbing iodine there. Iodine likes to ignite around 190 degrees Celsius. We're sparging from 650 degrees Celsius. We need to make sure that we're not anywhere close to 190 when we adsorb there. We also need to make sure we're not dealing with temperatures that are too low. Shouldn't be a problem, but if we are dealing with temperatures that are too low, rapid expansion of the oxygen at those temperatures could lead to explosion.
All right. The final separations or the final process step that I'm going to have you sit through is just a quick discussion of the heat management and power extraction loop. As I mentioned previously, this is almost entirely using the existing infrastructure at the Massachusetts Pilgrim plant. Reacting approximately 10 kilograms of actinides per day is the rate at which we're going to be processing the fuel. That allows us to actually process about a ton of actual spent nuclear fuel, SNF rods per day. All of that fission releases approximately a thermal gigawatt of power, half of which is removed as process heat to be used in other parts of the system and maintaining reactor temperatures throughout all of our separations steps in the solid separations. We are still using, although we are drastically underusing the existing turbine infrastructure at the plant. The turbine is able to produce up to 700 megawatts of electrical power. We'll be producing around 100 to 120 megawatts, which will all be used on site to power our various systems, to power the rest of the plant, as well as all of the safety features. The rest of the heat will be extracted through the cooling tower and cooling infrastructure already on site at the plant, although pretty significant renovations to that system will need to be done, including addition of a forced cooling system in order to extract the 380 megawatts of thermal power that is still needs to be bled out from the reactor. For controls, as I mentioned at the very beginning of the process talk, the control rate of the heat extraction step is all fundamentally designed to keep the molten salt reactor at its highest optimal criticality temperature. And everything else controls-wise in our system is chiefly to ensure pressure regulation and safety of all of our heat extraction loops.
So, in our whole process, we're dealing with very caustic and very corrosive materials. In order to make sure that we have the highest level of safety possible, we need to take a lot of thought into the materials that we select to construct our processes. For our reactor vessels and our piping metals, we chose between 430 stainless steel, Hastelloy-N, and Hastelloy G30. And for 430 stainless steel, it is easily corroded by molten salts. And Hastelloy-N, although it was used in the Oak Ridge National Lab experiments early on back in the 50s and 60s, we found that there were significant deposits of metal on the inner parts of the piping, and therefore led to system inefficiencies. So therefore, we decided to go with Hastelloy G30, which is an alloy that is actually built off of the Hastelloy-N and has significantly shown to reduce these deposits. For the molten salt, we have various lithium and beryllium compounds, as well as other alkali metals. We decided to go with FLNAC because FLiBe, which is lithium fluoride and beryllium fluoride, is very toxic to humans, and we need to ensure the safety of our operators. And the reason we did not select FLNARB is that FLNARB does not actually have as high of a heat capacity and is not able to generate as much heat and steam for our power extraction and our heat removal steps from the molten salt reactor as FLNAC. And finally, for our neutron moderator, we decided between graphite, magnesium hydride, and zirconium hydride. Graphite is not compatible with molten salts, and although magnesium hydride initially seems like it may be a better material for our system based off of some research, zirconium hydride has a much more demonstrated ability to be used in a molten salt system, and therefore we decided to go with that.
So at the end of the day, we've gone through all this research, we've gone through all this development, but we're just like any other company. We're looking to provide a service at a profit. So in order to do that, we need to do three things. We need to figure out what we're getting ourselves into with a market analysis. We need to come up with a funding timeline and a business model. So here's our market analysis, and basically what we found looking into this is we found virgin soil. This is new territory, ripe for a business to come in. So currently, the current standards, as David mentioned earlier, involve three different processes. Mass Pilgrim is currently looking to go through SafeStore, and what that means is they're spending about $7 million a year to house these materials. Now that's done for about 70 years, and at that point, nobody really knows what to do with the spent nuclear fuel. So they're just further kicking that can down the road. But when it comes to shutting the whole plant down, that's another $1 billion on top of the accumulated costs. So if we can be competitive with this and come in well below that, we should be able to take up a lot of that market share. The other benefit is, as we all you know, get used to our new phones, computers, society grows, yeah, so does the energy demands. So as you can see, about 20% of the United States energy comes from nuclear, and that market is expected to grow to about $300 billion a year. So what this does is it provides benefits and advantages to our company. So we sort of hit the holy trinity in the business world. We can do it better, we can do it faster, we can do it cheaper than anybody else out there. So coming in on the cheaper side, we're about a third the cost, so a third of $1 billion. We actually take care of spent nuclear fuel. So that's pretty much, that's the big part, is we don't have all this nuclear material lying around. And we dramatically reduce the timeline. So instead of keeping this material in a pool for 70 years and then trying to figure out what to do with it, in 7 years, we've taken care of that. And the advantages we have, as I said earlier, this is a new market, right? So currently there's one company, maybe a few out in France who are pyroprocessing, but in major markets and major emerging markets, such as the United States, India, and China, there really isn't anything going on there. So that is an opportunity that we have where we can go in there and dominate that market and dictate the future of pyroprocessing of spent nuclear materials, which results in a large return on our investment, which is what we all want to do, is make money. So for our funding timeline, nuclear materials are not cheap. So in the first 3 years, we're looking to secure $150 million. We're looking to secure $150 million over 5 years. The lion's share of that, $120 million, looking to get the first 3 years to get us up and off the ground. So we're looking to retrofit Mass Pilgrim, and again, that'll cost a significant share of the 120, as well as personnel. This 120 million is looking to come from two primary sources: the Office of Regulatory Financial Assistance Program, which is a government agency developed to help people like us, so new companies that are looking to improve the safety and the environmental impact of nuclear energy, because the government, again, really wants to keep an eye on nuclear material, and you can't really blame them. The second source is Breakthrough Energy Coalition. This is a coalition of very wealthy individuals who are looking to change, who are basically concerned with climate change, right? So to get us off the dependency of fossil fuel, people like Bill Gates, those sort of people, the CEO of Amazon. From there, the fourth and fifth year, we will be taking the next 30 million of our venture capital just to prop up any remaining costs, as well as to supplement our labor costs for the operation of the plant. So to cover this, we get to our estimated cost of production. We're looking to employ 100 engineers at $90,000 a year and 150 technicians at $60,000 a year. This works out to about $18 million a year in labor costs alone. Couple this with our ISBL, our OSBL, our overhead costs, our contingency costs, our outstanding engineering costs, our utilities costs, and it works out to a fixed cost of $54 million. This, coupled with our variable cost of $53 million, the variable cost is quite significant due to the fact that we're using very unique materials in very large quantities. So it's not cheap to source that. Comes to a combined cost of $107 million. What we're looking to do is, since, like I said, it's a very new market, we have the ability to demand market share. We're looking to make 30% gross profit on that with a lower threshold of 20%. $212 million. And the way we achieve this is charging $786,000 per ton of material. Ton of material a day, 270 days a year. It adds up. So here's our business model. So our business model is a 10-year cycle. So it takes us 7 years to produce, to process material, and we're doing this on site. So we need to spend the first 2 years to establish our reactor in the existing plant's infrastructure, further 7 years to process, and then a year for cleanup. And again, you can see our profit chances and our cost per ton of material, and what this works out to is a 10-year NPV, or net present value, of $243 million. The big number there being the return on investment at the bottom. We're looking at a 41% return. Our break even is 4.7 years. This is including the 2 years of start time, because the second we flip the switch on this reactor, we can start making money. So the sooner we can do that, the better. And again, all this net income works out to paying dividends to our investors and returning them at a 30% leap.
So some of the safety, health, and environmental regulations surrounding nuclear reactors and the nuclear reactor business. In terms of transportation and security, for nuclear fuel transportation, we already established that we are able to get unused fuel from our reactor that it can be reused at other facilities once it's put back into fuel rods. This needs to be transported to that facility, which would be transported in large Type B packages such as this. These are 10-inch thick stainless steel vessels which transport nuclear fuel around the country and have never been ruptured or broken open to date. Security, we would be implementing the existing security at Pilgrim, but just a quick so G4S Regulated Security Solutions is an example of a security company that provides security of the nuclear fuel at different reactor sites. And then for the regulatory process, all of our regulations are going to fall under an umbrella regulation called Part 52. Part 52 essentially wants all the licensing and regulations done before the reactor is built, and this will need to be done before our plan is up and running. So now we have PPE levels. These are the official OSHA and EPA regulation levels for different environmental hazards. So we have a level A through D, A being the most hazardous, D being the least hazardous. When we're going to be working with the highly toxic and highly radioactive areas in our facility, we're going to be using level A. This is completely airtight, allows for an hour air. And then it can also be lead lined. This will prevent and reduce the amount of radiation the person receives. And then depending on other work that's being done, they could be using something such as level C, which is just a regular hazardous waste suit with a mask, and that's used for when the concentrations are known. And then depending on anywhere in the lab area / reactor area, anywhere anyone's doing work, they're going to be using dosimeters, this is an example of a badge dosimeter, and depending on how long they're there, there's different regulations that OSHA mandates for how much radiation a person can receive. So waste disposal. So we talked about where we're going to go and how we transport the unused fuel, the fuel that we retain to transport it to make new nuclear rods. But we also have that leftover stuff that still is going to take about 100 to 1,000 years before it's not radioactive. So this needs to be handled, and this is going to be handled through vitrification, which we talked about before, which is just encasing it in glass and letting it sit there and be less radioactive over time. And then in terms of our actual system, all the pipes, tanks, and whatnot, these are going to be radioactive after our process, and we're going to be consulting with Battelle, which is a large engineering firm, and they have numerous expertise projects in different things such as the Hoover Dam, and they helped construct the first nuclear reactor in the U.S., and they also were the ones that were constructing Yucca Mountain, which was going to be the U.S. repository for spent nuclear fuel. And then here's just an example of our failure mode analysis and what could go wrong and what are the chances of it going wrong. As you can see, the main thing that we were concerned about was corrosion, because depending on where the corrosion is taking place, it's hard to detect if there's corrosion taking place, and it would be a very large impact if it happened to leak. So we took care of this problem by using the best alloy that we could find, which is Hastelloy G30. And then last, on the next page, we have this is a sample piece of our HAZOP analysis, which essentially just shows, essentially the same thing for almost every case, where if you have no flow or less flow for your sensor, then you know that something is wrong and there needs to be more flow, otherwise there could be leaking before, there could be a blockage, and if you have too much flow, you could potentially have leakage in that reactor area.
So, in summary, we have significant market demand for nuclear energy. We show that we are able to enter this market with very little competition and also a lot of potential growth. Our technology reduces the half-life of nuclear waste from hundreds of thousands of years to tens, hundreds, or thousands of years, reducing and eliminating the various amounts of waste that are currently spread around the country. And finally, our novel separations processes are able to take uranium oxide from nuclear reactors and recycle it such that we can generate more electricity, so that we can have overall more low carbon energy and mitigate the effects of climate change.
So that's our project, and we of Renuclear would like to quickly just thank the people who have helped us. We would first and foremost like to thank Oak Ridge National Laboratories and their partners at Union Carbide Corporation and the MIT School of Chemical Engineering Practice for the immense amount of work that they did in the 60s and 70s, a lot of which is published online and available for free use, and it has helped us significantly in overcoming technical challenges. We'd also like to thank Mr. T. Bond Calloway and Mr. Mark Williamson, who served as technical mentors on the project and helped us with the initial conception of the project, as well as our business mentor, Ms. Nicole Williams.
Any questions?
So the floor's open for questions. We'll give you a minute or two, but excellent. Any questions? Pausing for a minute. Go ahead.
It sounds like a complicated and potentially hazardous process, and permitting, I would imagine, would be quite a big issue. Did you estimate how long the permitting process would take, and did you build that into your business plan?
Yes, so we are basing it off of previous business plans, like we had mentioned earlier with Vermont Yankee, as well as Pilgrim Nuclear. They have already gone through the regulatory process, and because this would be included in future plans in terms of when the decommissioning process is set in plan, usually these processes are usually taken into account when the actual nuclear plant is operating. So if there's a planned decommission 10 years beforehand, this is already part of that plan.
So the chemistry caught my interest. You're taking uranium F6 over to uranium F4 with hydrogen. Who was your consultant on that, and where did that idea come from?
A lot of that is based on work that was done at Oak Ridge National Labs in the 60s and 70s. They demonstrated quite a few different ways to deal with a lot of the gaseous products that you're dealing with, as well as separating out some uranium from the SNF itself.
And a lot of this was also corroborated by recent studies done in the past decade or so of scientists and engineers who have continued the work.
Okay, so I would comment, you're producing on that hydrogen fluoride,
Yeah.
which is a nuisance.
Sure.
Could the sodium cadmium be used in place of hydrogen? So you make sodium fluoride, which is pretty inert. Do you know if that's possible? Or?
I do not know if that's possible. One thing to note is that there are many places in our process that actually demand hydrogen fluoride as a way to convince uranium and protactinium, for example, to come out of other salts. So that it's very useful to have some hydrogen fluoride if we can properly take that and recycle it in a safe way. I'm not sure if sodium can be used in place.
All right, any other questions? All right, thank you very much.